In today's video, we're going to be talking about friction. After watching this video, you should be able to understand what friction is and know the formula for calculating frictional force. So let's get right into it. The first thing I want to talk about is friction is a force, and we've mentioned that before in some previous lessons that friction actually is a force, and it's a force that basically opposes motion. That's the job of friction. And there's really two types of friction that you should be aware of. The first type is called kinetic friction, and kinetic friction opposes the motion of an object that's sliding along a surface. So if you can picture yourself sliding a box across your kitchen floor, the friction that's going to oppose your motion of sliding that box across the kitchen floor is going to be called kinetic friction. Static friction acts on objects that aren't yet sliding. Okay, so let's say you have a box on your kitchen floor and you want to start to get it sliding across the floor. To get that box into motion, you're going to have to overcome the force of static friction. And typically, it's harder to get something started, so the static friction is usually bigger in terms of force than, say, kinetic friction, typically. Just because, and you probably have experienced this firsthand, where once you get something kind of moving, once you get it sliding, it seems to be a little bit easier to push it along whatever surface it is you're going on. So this is just kind of a microscopic picture. Here's just a big old block of something, and here's a surface that's sliding across. At a microscopic level, nothing's perfectly smooth, and so these little ridges and joints and crevices and cracks basically run into each other, bump into each other, and that is what causes friction to occur. It's going to oppose motion. So how much friction is created from various surfaces is determined by, one, the nature of the surface. And the nature of the surface is given a value, and it's called the coefficient of friction. And that symbol is this little weird looking U, and it's pronounced mu, M-U, and that is called the coefficient of friction. And that's typically something you're just going to look up. And then the other piece that goes into how much friction is created is the normal force acting on the object. Okay, so how much is the kitchen floor pushing back on the box, or how much is the table pushing back on the glass that you're sliding across the table, or whatever the case may be. So it's a combination of the normal force and the coefficient of friction. So the coefficient of friction is a ratio of frictional force and normal force. And typically, not always, because sometimes I'll ask, can you calculate the coefficient of friction? But typically, it'll be a value that I either give you or I might ask you to look up. So if you look in your books, you'd find a chart or a table on page 129 that's divided into sliding or kinetic friction and static friction. There's two types of coefficients of friction, and so there's different numerical values for different surfaces. And they give you, like, I don't know, 6, 7 different common surfaces that you might see with problems, like asphalt or sand or whatever the case may be. I don't have the chart right in front of me, but basically it gives you some numerical values of the coefficient of friction for different surfaces. And like I said in the previous slide, almost always there's less friction for sliding an object than one at rest. So once you get it sliding, typically it's easier to keep pushing it than, say, starting it from rest. This down here is a formula to calculate the coefficient of friction. So it's mu equals the force of friction, that's a big F with a little f as a subscript, over the normal force. So mu equals the force of friction divided by the normal force, and that'll give you the coefficient of friction. So if I ask you to calculate it, that's the formula you'd want to use. So calculating the force of friction depends on the type of surface the object is in contact with, and that's the mu piece, and the magnitude of the normal force. And so that formula I just showed you in the previous slide, basically I just reworked it around to get force of friction by itself. And here you have force of friction equals mu times the normal force. This formula you probably will use a lot more than the previous one. But they're both actually, they're the same two formulas, just moving things around a little bit algebraically. Okay, so I'm going to give you an example problem in just a second here where this formula we won't actually use it per se, but it could have been used. And it comes down to drawing good free body diagrams and thinking about Newton's second law. And using those free body diagrams and Newton's second law will kind of help us solve more complex problems, because now the force of friction is going to start to come into play when we try to calculate the net force on an object. All right? So here is an example problem. Let me change pen colors here. Let's do, I think green's visible. So it says a force of 50 newtons is applied to a 4 kilogram box. The box accelerates 10 meters per second squared on a rough horizontal surface. What is the magnitude of the frictional force acting on the object? Okay. As always with these problems, I highly recommend starting with a free body diagram. Okay, a free body diagram. So here's my box, and I'm actually drawing a real box. And the first force I always want to draw is the force of gravity or the weight. Okay, force of gravity or the weight. Okay, that's always going to be in existence. Okay. Now it says it is sliding across a rough horizontal surface. So I'm just going to draw that surface in right there. Now, what is going to oppose the force of gravity? Well, that is the normal force, F sub n, the normal force, right? Now, because the box isn't, like floating upward or smashing through the rough horizontal surface, we probably can make the assumption that these two forces, the normal force and the force of gravity, equal each other and they cancel each other out. So they are not going to play a role in this problem, at least from what I've read. It doesn't appear that way. Now, it does say that this box has a mass of 4 kilograms. I'm just going to write that on the side here, just so I know. Mass equals 4 kilograms. And there is an applied force, so F applied of 50 newtons. So I'm going to write F applied of 50 newtons. What is the magnitude of the frictional force acting on the object? So remember, frictional force opposes motion. And so I'll draw that over here. We'll draw big F, frictional force, opposing this motion. Okay? So like I said, the force of gravity and the normal force are going to cancel each other out because there's no acceleration in the vertical direction. Basically, the box is not moving up or down. Now, clearly, the applied force must be overcoming the frictional force because the box is accelerating. Okay, and acceleration indicates that there is a net force that's present. Okay, so what we're going to use is we're going to use Newton's second law, and I'm going to change pen colors here just to get something a little bit different. Let's use cyan. And basically what we're looking at is we're using Newton's second law, F net, and this Newton's second law, we're only looking at the stuff in the x direction. So I'm going to label that as such. F net in the x direction equals mass times acceleration. All right. Now, we haven't really gotten into this too much yet, so if you're freaking out, don't worry. The very next lesson's actually right about this, but I'm just kind of giving you an example problem of dealing with friction. So F net in the x direction equals mass times acceleration in the x direction. Now, what is my net force in the x direction? Well, I have F applied minus the force of friction, right? Those two forces are kind of competing against each other, equals mass times acceleration in the x direction. So what is F applied? Well, F applied is 50 newtons, right? So I'm just going to fill that in here. 50 newtons minus the frictional force equals the mass is 4 kilograms. And the acceleration, I should have written that up here with this stuff just so you'd have it, is 10 meters per second squared. All right, and then basically if you just do this algebra where you take 4 times 10, which is 40, and subtract it from 50, you get negative 10. But there's a negative in front of the force of friction, and so really the negatives cancel each other, and you would get a frictional force of basically 10 newtons. Okay, that is the magnitude of the frictional force acting on the object. And because we drew this awesome free body diagram, we could say 10 newtons to the left because it's going to oppose this motion that we just kind of arbitrarily set up saying, well, it's going to be going to the right. And again, if you don't get this problem, don't worry. We haven't really done Newton's second law problems. I just wanted to kind of give you a preview, if you will, of how friction interacts with dealing with free body diagrams and calculating the net force. That takes care of this video. I will see you guys next time.